Thank you very much. Thank you very much. I'm recording now. So I was still saying, we looked at that example of studying the relationship between the hours spent on a study and the exam score. So what we want to achieve at the end of the day is to predict the exam score given the hours once spent preparing for that particular exam. And then after that, we looked at a simple linear regression model defined there, where we said a linear or a simple linear regression model is yi, or given by yi, which is equal to beta 0 plus beta 1 xi plus ei for I is equal to 1, 2, 3 up to n, where yi is the value of the response variable for the ith observation. So if we have, for example, we have a group of students from this class, we want to study the relationship between their exam score and the hours they spent preparing for the exam. So the yi will be representing the students. So if the first student, for example, is Chabalala there, it means y1 will be the exam score for Chabalala, because the exam score in that example is our response variable. So y1 will be the exam score for Chabalala if Chabalala is the first student. And then y2 will be the exam score for Humu if Humu is the second student, and so forth. So xi is the value of the independent variable for the ith observation. So x1 will be the hours spent by Chabalala preparing for that particular exam, and x2 will be the exam, will be the hours spent by Humu preparing for the exam, and so forth. So beta 0 and beta 1 are the parameters of the model. Yesterday I mentioned that you should revisit some of the things you covered last year, so that you can follow when we are doing these things. I said yesterday that we are not going to look at all the things that you covered, but we looked at some of the things that you are going to need in the module, and I asked you to go and look at the other things that you have covered. So beta 0 and beta 1 are the parameters. You know what is a parameter, and EI, or the EIs, are the errors, or EI is a random error term with the properties listed there. The first one is that the random error term has a mean of 0. So the expected value of the error term is equal to 0. And the variance of the error term is constant. So it's sigma squared. As you can see, the sigma there does not have a subscript, which tells us that the variance is constant. So the variance of E1 is the same as the variance of E2 is the same as the variance of E3. So the variance is constant. And these errors, EI and EJ, are uncorrelated. So for I not equal to J, then the covariance of EI, EJ is equal to 0. So the covariance of EI, EJ is equal to 0. For I, it's not equal to J, because if I is equal to J, then the covariance of EJ, EJ will be equal to the variance of EJ, and that will give us sigma. So the covariance of EI, EJ, where I and J are not equal, it's equal to 0. But in a situation where I and J are equal, then that covariance will be equal to the variance of the errors, and that will be sigma. Then the last one is that the errors are normally distributed are normally distributed. So we know the mean and the variance now. So we can clearly, or we can state that the random error term are normally distributed with a mean of 0 and a constant variance sigma squared. Is it clear? Is it clear? Thank you very much. So now let's look at this. What are these errors? What are these errors? So let's have a look at this. You remember this from yesterday. We had this scatter plot. Then we were studying, or we are still looking at the relationship between the exam score and the hours there. So the exam score on the y-axis and the hours are on the x-axis, because these are the hours or is the independent variable. So we have the scatter plot there and the line, the fitted regression line and the fitted regression line here. And now the question is, what are these errors? So if this was a perfect fit, then all these points were supposed to be on the line. But as you can see, not all the points are on the regression line. I can hear that you are typing something. As I've said yesterday, that when I'm projecting the whiteboard, I'm not able to see what you are typing. So if you have something, please raise your hand so that I can recognize you, because I cannot see what you are typing when I'm on the whiteboard. So now you can see that.
Mr. Maral?
Mr. Malega?
It's me. I wrote something there. I will rejoin at 8:55 to greet the readers.
Okay, okay. Thank you. Thank you. No problem. Thank you very much. So as I was saying, that not all the points are on the regression line, then we talk about these errors. So if you look at the first point, for example, it's very close to the line, but it's not on the line. And if you go to the second one, it's also not on the line. So the question is, what happened here? Why is this point not on the line? And the same applies to this. It's also not on the line. Even this one is not on the line, and this one is also not. So you can see a majority of these are not on the regression line. And these are the errors that we are talking about there when we say the model is yi beta 0 plus beta 1 xi plus the errors. So these are the errors that we are talking about. So that distance from the line to this point here, it will be our E1, and then this one will be our E2. So what we are saying there on these properties is that this will be E3, E or epsilon 3, because it's not an E, it's an epsilon. So this is epsilon 4, epsilon 5, like that. So what we are saying that there is that the mean, the expected value of these errors, it's equal to 0. So if now you know the values on the line, if you know all these values on the line and you know the actual values, you can calculate the errors. And when you have the errors, you can calculate the mean of these errors, and they have to give you 0. So that's what we are saying there when we see the errors are normally distributed with the mean of 0 and a constant variance. And when you come back and calculate the variance for the errors, the variance should be constant. So the variance of these errors is constant. And there's no relationship. These errors are uncorrelated. So the covariance of these errors is equal to 0. So which means now if we want to calculate these errors and we have the actual value of y, then we can also calculate this. And what is this? This gives us the values on the line. These are the expected value of y for a given value of x. So this is an expected value of y for given value of x. So we can calculate the expected values. So when you calculate the expected values, the chances are that not all will be equal to the actual values. That's why we're having these errors. So our error term is nothing but the actual value of y minus the expected value of y for some given value of x. So these are our errors. So our errors can be calculated using that expression there. So EI is equal to YI, which is the actual value of the response variable minus the expected value of the response variable. Is it clear? Thank you. Let me project the notes. So you can look at these properties or this model. You can use the graph to look at this model. So the equation, which is yi is equal to beta 0 plus beta 1 xi plus ei, is called a simple linear regression because it has one independent variable. So it is simple because it has one independent variable. So it is simple because of that. And this tells us that the first example that we looked on, which is this one, because here we're having two independent variables, then this is not an example of a simple linear regression model. So a simple linear regression model has one independent variable. And it is linear because there is no parameter that appears as an exponent or a parameter that is multiplied by another parameter or divided by another parameter. So as you can see, we have two parameters with no exponents or multiplied or divided by another parameter. So it is linear because of that reason. And it is simple because it has one independent variable. So that is why it's called a simple linear regression model. Now, the observed value of y, the observed value of y for the ith observation is the sum of the two components. So what we are saying here is that the value of y is the sum of two components. The first component is this constant, because if we know the value of y, the value of x, if we know the value of x, then this becomes a constant, this becomes a value, and plus the error term. So y, it's a sum of two components. Yi is the sum of two components, which is the constant term and the error term. So our observed or our response variable it's a component of, or it's a sum of two components, the constant term and the error term. And if that is the case, now let's go back to this. If that is the case, it tells us, because if you look at this, let me change the color. If you look at this, one here, is the constant part, of the model, which tells us that our model yi is equal to the expected value of y plus the error term. So now we want to do this. We have our model, yi, which is equal to beta 0 plus beta 1 xi plus the error term. Now, we know that the expected value of yi is equal to beta 0 plus beta 1 xi. Or we can just show it here that the expected value of yi is the expected value of the entire function, which is plus ei. And we know that this is a constant. And yesterday we said the expected value of a constant is equal to what? So we can write this as, because our yi is a component of, or it's a sum of two components. So the first one, we have the expected value of that plus the expected value of the error term. And this is equal to, the expected value of a constant is a constant. So we'll have this constant plus the expected value of the error term. And we know that the mean of the errors is equal to 0. And this becomes 0. Yes, you are recognized. You are recognized, Tato.
So are you writing on a what?
Sorry about that. Let me project the. So guys, please, as I've indicated, when I'm on the whiteboard, I cannot see the comments or the messages you are typing. So please raise your hand so that I can recognize you. Please don't type when I'm on the whiteboard because I cannot see. So let me start here. I will just delete this. So what I was saying is that we have our function yi, which is equal to beta 0 plus beta 1 xi plus the error term. So we know that yi is a sum of two components, the constant and the error term. So the expected value of yi, yes?
Mr. Chair. Oh, sorry, sir. You didn't project again.
Even now it's not there. I cannot see the messages. Please use the mic.
No, sir, it's not there.
Okay, let me do this. What about now?
Yeah, it's fine.
Thank you very much. Let me start. So we are dealing with a simple linear regression model given by yi, which is equal to beta 0 plus beta 1 xi plus the error term. So we know that beta 0 plus beta 1 xi is the constant term, and the last part is the error term. So now we want them to find the mean of yi, which is equal to the expected value of the constant plus the error term. So yesterday we discussed that the mean or the expected value of ax plus c is nothing but the constant multiplied by the expected value of y plus the constant b. So we're going to have the same here because this is a constant plus the error term. So what we're going to have is the expected value of xi plus the expected value of the error term. And the expected value of a constant is a constant. We discussed this yesterday. So the expected value of a constant is a constant plus what is the mean of the errors? We know that the error terms are normally distributed with a mean of 0 and a constant variance. So this mean is 0. And then now we have this. So the expected value of y is nothing but beta 0 plus beta 1 xi. Is this clear? Is this clear?
Yes.
Yes.
Thank you. Thank you. So now let's look at the variance of the model, which is yi beta 0 plus beta 1 xi plus ei. So the variance of this is equal to the variance of y, and our y we know it's equal to beta 0, beta 1 xi plus ei. And this is equal to the variance of beta 0 plus beta 1 xi plus the variance of ei's. And what is the variance of a constant? The variance of a constant, as discussed yesterday, is equal to 0 plus the variance of the error term. And the variance of the error term is equal to sigma squared. So the variance of sigma squared of yi is equal to 0 plus sigma squared, which is equal to sigma squared. So now we know that the mean of the response variable, which is yi, is equal to 0, and that the variance of the response variable yi is equal to sigma squared. Again, we know that yi, which is this term, I mean ei, which is this term, it's normally distributed. We know that yi is normally distributed. So, I mean ei is normally distributed. And yi is a linear function of a normally distributed random variable, because this is a normally distributed variable. So we know that yi is a linear function of a normally distributed random variable. And because of that, yi is also normally distributed. So the reason why I now is normally distributed is because it's a linear function of a normally distributed random variable. Those who, you all know this. When you standardize, you say z is equal to x, then you subtract the mean, and then you divide by the standard deviation. And this can be written as 1 over sigma xi minus mu over sigma. And x was a normally distributed random variable with a mean mu and a variance sigma squared. Then we say z is also normally distributed with a mean of 0 and a constant variance. The reason z is normally distributed is because this is a linear function. As you can see, this is our a and this is our b. So it's more like we're having ax minus b, which is a linear function. So z here, we are saying is normally distributed because it's a linear function of a normally distributed random variable. X is normally distributed. So we are using the same logic here, that EI or EI is a normally distributed random variables. The errors are normally distributed. Then because EI or YI is a linear function of this variable, which is normally distributed, then this one also must be normally distributed. So the YI's are also normally distributed with a mean. The mean is beta 0, 1 xi, and the variance is sigma squared. And because the EI's are uncorrelated, then the YI's are also uncorrelated. So the covariance of YI, YJ is equal to 0. The covariance of YI, YJ is equal to 0. For I is not equal to J, because if I is equal to J, then the covariance becomes the variance, and that will be equal to sigma squared. That will be equal to sigma squared. Is it clear? Is it clear? So that explains this whole paragraph that that is highlighted there. So what I was doing there explains this entire paragraph that we're discussing. So this information is not, yes, I'm recording. This information, people, it's not in the guide, but this paragraph is there in the guide. But what I'm saying, why the YI are normally distributed, is not in the guide. So because I'm saying this, there are people who after class will say, sir, can you please provide the things that you were saying? I don't have them. I don't have a piece of paper with these things written down. So that's why I said yesterday, classes are important so that you can get this information. So those who requested the notes, I don't have these things written down. I don't have, but the things that I have projected are there in the guide. The things that I have projected are there in the guide. So now we have an example here. We're saying consider a simple linear regression model with a normal random error term. So you have a simple linear regression model with a normal random error term. So this statement is very important here. If the error terms are normally distributed, it means the response variable is also normally distributed. And the error term meets all the assumption. So it means the mean of the errors is equal to 0, the constant is, the variance is constant, and the covariance is 0, and that these errors are normally distributed and they are independent. So that's what we are saying there by that statement, that the errors meet all the assumption. So suppose that the parameter values, so beta 1 is 210, beta 1 is 3.9, and the standard deviation, which is sigma, is equal to 5. Then write down the model of y for these values. Write down the distribution. So the first thing that we are going to do, here, again, this example is not there in the study guide. So if you want this, I'm recording the session, so you can get this. You can get this. I mean, in the recording. So we have this example. Let me project the whiteboard so that I can write. So we have this example. We have our response variable yi, which is equal to 210 plus 3.9 xi plus the error term. So what we want here, we want the distribution. We want to write down the distribution of y for the given values of x. We want to write down the distribution of y for the given values of x. Let me just check those x values quickly. So it's 10, 20, and 40. So we have 10, 20, and 40. I want to believe that you can see the whiteboard. So we have the x values. So what we want first, because we know that the variance of EI, for example, we know that EIs are normally distributed with a mean of 0 and a variance of 25. We know this. And this tells us that the variance of YI, this tells us that YI is also normally distributed with the mean that we don't know and the variance of 25. Now, we want the mean of Y for the first one. So the mean of Y, the expected value of Y for X, the mean of Y is given by beta 0 plus beta 1 xi. So now we know our beta 0 is 210 plus 3.9, which is our beta 1. And for a given value of x, now we're given that our x is equal to 10. And this tells us that the expected value of y for x is equal to 10. It's nothing but what? 249. And we can now calculate the expected value of y for x is equal to 20. And that will be 210 plus 3.9 multiplied by 20. And that will give us 288. Then we have the last one, which is the expected value of y for a given x is equal to 40. And that will be 210 plus 3.9, 40. And this will be, I cannot see what you are typing. So that's why I'm not replying. And this is 366. So the first one, the distribution of y for a given value of x, which is 10, the first one, it means y is normally distributed with a mean which is equal to 249 and a variance of 25. And the second one, which will be y2, is also normally distributed with a mean 288 and a variance of 25. And the last one, which is Y3, is also normally distributed with a mean 366 and a variance of 25. So those are the distributions of Y for the given three values of X. So these are the three distribution of Y. These are the three distribution of Y for the given value or for those given value of X. And the following question is that we have to find the errors given these to be the actual values. So we want to find the error term for these actual values. So now we know the actual value of Y when X is equal to 10. So when X is equal to 10, the actual value is 245. Is 245. So if that is the case, now let's do this. If that is the case, now let's go back to the whiteboard. 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 We are here. So we know that for X it's equal to 10, the expected value, because remember we said note these values, please note these three values, note these three values, note them. Remember we said the expected value, because we want, the errors, it's equal to the actual value or the observed value minus the expected value for some given value of X. And the first one, the actual value that was given is 245 minus the actual value we are told is, the expected value. You are recognized. You are recognized. Silo.
Sir, okay. Yes, sir. Okay. Mine is that there where now we are defining the position J. The expected function. We estimated the expectations. Yes, sir.
I think we're even out of time. Yes. I cannot hear you.
What I want to know, sir, is that are we estimating the expected prediction function at a particular value?
We are not yet estimating the function. We are calculating the mean. We are calculating the mean. Let me.
We are still under assumptions. We are still under assumptions.
Yes. So we are not yet estimating the function. We are not yet estimating the function. Can you see the whiteboard?
Yes.
Thank you. We said our function, it's yi, which is equal to beta 0 plus beta 1 xi. This is the constant term plus the error term. And from this, we said our error term is nothing but yi minus the constant term, which means if we know the actual value of y and we know the value of the constant, then we can calculate the errors. And when we were looking at the expected value of y, we said the expected value of y, I'm not going to repeat the steps. Then we ended up with this when we're looking for the expected value of y. And this tells us that the expected value of y is equal to this. Because if you look at the error term, it's equal to yi minus the constant term. And when we calculate or when we're looking for the expected value of y, we ended up with the error with the constant term. So this tells us that this constant term is equal to the expected value of y. So if, for example, we know the value of x here, if we know the value of x, because we're having the parameters like this and the value of x. So if we know that particular value of x, then it means we can get the expected value of y. And that's what we did. We calculated the expected value of y for x is equal to 10. And that was 249. So this tells us that the error
Leaders.
we want to feed the regression line,
That's fine.
and the data points should be on the line. And you saw on that first scatter plot that not all the data points were on the line. So which means there is that error, and that's what we are trying to calculate here. What is the distance from the, yes, Tinigo, you are recognized.
Sir, can you please go back because you were reconnecting? We couldn't hear what you were saying.
I'm sorry about that. We are out of time. Let's stop here for today. Then on Thursday next week, we'll start this example from scratch. So let's stop here for today, and then we'll do that example again on Thursday. So Mr. Malek is with us, as I promised yesterday that those who don't know him, he will be here to greet you. So before you leave, Mr. Malek, over to you.
Thank you, Mr. Malala. Good morning, leaders. You are welcome. For those who don't know me, we will meet in a later stage, not now. Now enjoy the module with Mr. Chabalala. I will join you guys soon when Mr. Chabalala is done with his part. I thank you. Enjoy.
Thank you, Mr. Malek. So guys, we are done for today. Yesterday I said our classes will be on on Thursday, sorry. Then we are going to have the first class Monday 7:30. I mean Thursday 7:30. Then the second class again will be on Thursday 1 o'clock. Then on Friday this time we will not have a class, but we'll have a tutorial at 10 to 3. So please don't forget that. On Thursday next week,